Hi, it's Paul Andersen, and this is Science and Engineering Practice 4, Analyzing and Interpreting Data. After you've done an investigation, you're going to be presented with a lot of data, and it's important that you learn how to analyze that. In science, data analysis is important because it allows us to derive meaning from the data that we've collected, and in engineering, to test solutions to problems. And so basically, data analysis is important for the following reason. This is Charles David Keeling, and he spent his whole life collecting data on the atmospheric carbon dioxide, how much carbon dioxide there is in the atmosphere. And he did this on the Mauna Loa Observatory in Hawaii. And this is just a portion of the data that he collected as a scientist, just a few years, 58, 59, and 60. And when you look at this, it makes no sense to me and probably makes no sense to you. But if we organize the data correctly and we graph it, you get what's called the Keeling curve. This shows how atmospheric carbon dioxide has increased over time. Again, that's going to account for a lot of the global warming that we're seeing because a lot of that carbon is coming from us. And so it's important that we can put the data together and then present it in a way that we can make meaning from that. And so the goal in science classrooms is to analyze data. We do that by, first of all, organizing and graphing it, and then interpreting the data, making sense of the data, evaluating it, laying it against our theories, laying it against our designs, and then we can use mathematics and statistics to do a lot of that. And so the progression in school of analyzing and interpreting data really should start at the elementary level. And so again, it's like throwing darts, but getting better and better and better through the years. And so we can break this down by school level. In other words, at elementary school, students should be using a notebook, a science notebook, and they should be collecting data, and everything goes into that notebook. And that could be drawings, it can be numbers, it can be words, but they should get into this idea that they're collecting data and they're going to have to do something with that data. As you move through elementary, they should really get to the level of tables and organizing numbers and organizing data in a table. And so let's say you're doing an experiment on fertilizer and how varying the amount of fertilizer affects plant growth. And so they should get in the idea of using a table to organize that. And it's really good practice to always put the thing that you're changing or the independent variable in the first column and then dependent variable in the second. Graphing would be important at the elementary level. I think it's sometimes hard for students to figure out what kind of a graph should I use. And so you could give them quite a bit of scaffolding. You could say, I want you to graph it in a certain way at elementary level. But as they move into middle school, you really want the students to do the graphing on their own. And in my class, I use 4 different types of graphs I expect students to understand. And you should know this, that you're going to collect data first, and then you're going to have to figure out what type of graph to do. And so the data comes first, and so you really have to have an understanding of what kind of data you have before you can graph it. And so the 4 major types of graphs I teach are the line graph. We're looking at change over time, and you're going to connect the data points. We would use a scatter plot if we're looking at correlation of variables, so eruption duration and waiting time at Old Faithful. This would be a scatter plot. We're not going to connect the dots because we're just correlating those 2 variables. We would use a bar graph if we're comparing different groups, and then we'd use a pie graph if we're looking parts of the whole. And so you could present your students with data and first of all have them figure out, what kind of a graph am I going to use? As you move from middle school into high school, you want to make sure they understand the difference between an independent and a dependent variable. Independent variable, remember, is going to be the thing that you change in an experiment or I change in an experiment. Dependent variable is going to be what changes as a result of that. Scatter plots are powerful graphs when we're looking at correlation. So I could graph the data, and then you could get them, show them how to draw a line of fit or a curve of fit. Make sure that you start to teach the difference between causation and correlation. And so when you look at a graph like this, it looks like the fertilizer is causing the plants to grow more. You're not always sure, remember, and this is a good example you could share with your students. Scientists find that there's a definite correlation between the amount of ice cream that people eat and the amount of crime that is done in an area. So if you were to graph it, you would find that ice cream versus crime is going to be a nice kind of a relationship like that. It's correlation, though. It doesn't mean causation. Like, what's really causing this? Well, the warmer temperatures in the in the summer are causing people to eat more ice cream and causing people to commit more crimes in the summer. And so there'd be causation here, correlation here. And so you want to make sure when you're evaluating your data, really be hesitant before you jump into the idea of this is causing that. As you move to high school, you can really take a look at the mathematics and the statistics behind the data. And so a great example would be slope. So once we've looked at this correlation of the data, I could simply calculate the slope of that line of fit. So I could figure out the rise over the run, and I could figure out a y value of 0.4 centimeters per gram. And so slope is incredibly important, especially in a line graph when we're looking at change over time. Another thing that students don't usually understand in my class is what's called the correlation value or the R value. Correlation value, and you can do this in spreadsheets or on a TI calculator, basically an R value is going to tell you how good your data fits to a line if you do a regression. And so if in a linear regression you can have R values, like an R value of 0 means that there's no correlation between the two data sets. 0.6 means there's some, 1 means it's perfect. And we can also have negative correlation values as well. And so if you're to look up here, what is the correlation value? Maybe 0.7, something like that. And so students can actually start to look at their data and say, hey, how close is it to a line? How good is it? They're starting to then evaluate the data. You can move into the area of statistics then, starting with, let's say this is our data set here. Some simple statistics that I think are pretty powerful are the sample size, mean, median, and range. And so right here, the sample size would be 1, 2, 3, 4, 5, 6, 7. So there are 7 data points. That'd be my sample size. My mean or average is going to be 5. Add them up and divide by the total number. And then my median, to figure out median, would be right here. It's going to be in the middle. And if we were to have an even number, it'd be 5.5. You'll find that students are really good at this. Math teachers do a pretty good job at that. And my range right here would be 11. As you get more and more into statistics, you can move into the idea of normal distributions. I think standard deviation and standard error are incredibly powerful. I'll put links to 2 other videos I made on those. If you can get students to collect data and then look at the data, how good is this data? Then you're really not just displaying the data, you're really starting to evaluate it. And I hope that's helpful.